All right, our final series test here is the root test. And you are only going to use the root test when you have both the numerator and the denominator raised to the power of n. And what just happens in this test is, again, you have that row is equal to, you can take the limit of the nth root of the absolute value. And if it's between 0 and 1, convergent, bigger than 1, divergent, equal to 1, don't know anything. Okay, so let's look at this very first one. I notice that both my numerator and my denominator get raised to the power of n. Again, this is very similar to the geometric series, right, where we have like 5 over 6 to the power of n. Well, if that inside is less than 1, right, then we have convergent, bigger than 1, divergent. So now that this is a little more complicated, it's not just a rational number on the inside. I need to do a little bit more evaluation here. So I'm going to say the limit as n goes to infinity of the nth root. And then I'm going to just raise these both to the power of n. Since these are squared, and I'm only looking at positive terms, I don't really need the absolute value bars there. So these n's and the root cancel. I'm now looking at the limit of just the inside piece, which is a fourth, and that's less than 1. So converges by the root test. Let's look at problem number 2. Again, I'm going to write this as n over natural log of n to the power of n. These cancel. Oh, okay, what grows bigger, n or natural log of n? The answer is n, so this is going to be divergent. But if you need to use L'Hopital's rule, we can here. So this would be equal to the limit as n goes to infinity of 1 over n multiplying by the reciprocal. That just is n in the top. Well, that's going to go to infinity. So this is divergent, and then this one was convergent.